So we were looking at this particular statistical study where we were going to measure boredom tolerance. So Dr. Mendoza administered a test to a group of 20,000 adults between the ages of 25 and 35. The possible scores were 0 to 6, 6 indicating the highest. Now, for each score, so this is a discrete random variable because notice you have only 7 numbers starting from 0 until 6. For each number, you are listing out number of subjects. Number of subjects, this is not probability, it is simply frequency. Now, when I take relative frequency, that is each of these numbers divided by the total number of people studied, then you have what is probability distribution. For each value of the random variable, you have a probability. You add all these, you get 1. Now, these probability assignments make up the probability distribution. Notice that the scores are mutually exclusive. No one subject has 2 scores. That is, you see, these are mutually exclusive in the sense that if you have a subject here who has a score of 0, then that subject cannot have a score of 1 also. So you are allowed only 1 score per subject. All right. So the sum of all the probabilities is therefore 1. Okay. That's what makes the probabilities mutually exclusive. So all of these, for all these scores, you add them up, you get 1. You have no intersection values basically. All right. Now, here is the probability distribution. Probability distribution is another way of saying, in this particular case, relative frequency histogram. So this is the probability distribution, okay, which is the height of the bar over the score. For since each bar is 1 unit wide, the area of the bar over a score equals the height and thus represents the probability. Now this is important. Since the sum of the probabilities is 1, area under the graph is also 1. So, okay, look, the width here is 1, okay, negative. So, for each rectangle, the width by definition is 1. All right, the height is the probability. For example, for 3, height is 0.3. Okay, probability is 0.3. Now, what is the area of this rectangle? Length times width. So you know that the length is 1 and height is 0.3. So area of this rectangle is actually the probability at 3. The same holds for every rectangle. Area of the rectangle is the actual probability, which means what? Area of the entire shaded region is 1 because all the probabilities add to 1. So these areas add to 1. Okay, that's an important point to note. So area under the graph is also 1. Now here is another example continuing with the same example. The top-notch clothing company needs to hire someone with a score on the boredom tolerance of 5 or 6 to operate the fabric press machine. So this is a boring job. So you need someone who can tolerate boring work. So 5 to 6. So since the scores 5 and 6 are mutually exclusive, the probability that someone in the group who took the boredom tolerance test made either a 5 or a 6 or is probability 5 or 6. It is probability 5 plus probability 6. These are the numbers each. Add them up. Notice probability 5 or 6 We could have simply added the areas of the bar. Of course, 5 or 6. Area is probability at 5. Area of the smaller one is probability of 6. So you could have simply added these two. That's what they are saying. 1 out of the 10 of the group who took the boredom tolerance test would qualify for the position. So how did they come at 1 out of 10? Look at the probability 5 or 6. That is 10%. 0.1 is the same as saying 1 out of 10. Okay, 1 out of 10 of the group who took the boredom tolerance test would qualify. A probability distribution can thought of as a relative frequency distribution based on a very large n. As such, it has a mean and a standard deviation. Okay? If we are referring to the probability distribution of a population, then you use the Greek letter mu and for mean and sigma for standard deviation. When we see the Greek letters used, we know that the information given is from the entire population. Okay, so here is the mean and standard deviation formulas for probability distribution. The mean and standard deviation of a discrete population probability distribution. Okay, so we are looking at the discrete case. Mu is summation x times px. Mu is called the expected value. Sigma is given by the formula square root summation x minus p squared px. Sigma is called the standard deviation, where x is the value of a random variable, px is the probability of that variable, and sum is taken for all the values of the random variable. Note, mu is the population mean, sigma is the underlying population standard deviation, because sum is taken over all values. Okay? Now, the mean of a probability distribution is often called the expected value. So, for a probability distribution, the mean is called expected value of the distribution. This terminology reflects the idea that the mean represents a central point or a cluster point for the entire distribution. Of course, the mean or expected value is an average value, and as such need not be a point on the sample space. All right. The standard deviation is often represented as a measure of risk. So for probability distribution, you think of standard deviation as a measure of risk. A larger standard deviation implies a greater likelihood that the random variable x is different from the expected value mu. All right. So let's come to example 2 in our next video. Until then, bye.